actually my 3rd year at RubyConf Australia. It is my favorite conference in the whole wide world, like literally the whole wide world. So thank you so much for having me back and having me here. It's such a treat. Like Mel said, I'm an engineer at Heroku, and today I'm going to talk a little bit about distributed tracing. And I know it's like basically the end of the conference, and everybody is like super tired and really fried. I use a really cheap trick to like keep people awake, but also to encourage myself to drink water. So it's the worst thing ever, but I love it. So when I take a sip of water like this, I would like everyone to clap and cheer for me like I'm doing something awesome. So we're gonna try it out. Oh, thank you. Great job. Also, like Amy mentioned earlier, we ran out of Heroku swag, but if you would like us to mail you some, we will actually mail it to you if you go to this URL. And yeah, let's talk a little bit about distributed tracing. This is my team. I work on the tools team, and we spent some time implementing distributed tracing at Heroku for our internal services there. And I will say that a lot of the trial and effort and discovery that went into this talk was actually a team effort from these awesome folks. So let's start off with the basics, because actually I feel like a lot of engineers don't know what distributed tracing is, because I say, oh, this is what I'm talking about, and I get a lot of blank looks, which is great, because you are in the right place. So I just kind of want to get a little raise hands, who actually knows what distributed tracing is here? This is great, awesome. Okay, of the couple of people who do, how many have it at their company? Amy? All right, we've got a couple. So distributed tracing is giving us the ability to trace a request across a distributed system boundary. I'm going to give a simple use case. So let's say you have an e-commerce site, and you want to be able to show users all of the recent orders that they've placed on the site. So in a monolithic architecture, you have one web process. It's going to return information in that web request. You'll have users, they place orders have items, pretty standard Rails app kind of stuff. So we're going to authenticate our user, grab the orders and the items, render them on a page. Single app, single process. But because it's software, things always change. You get a mobile app. Suddenly now you need authentication on 2 different sites. So let's just break that out into a service. This could be running in separate processes on the same server, on a different server, or a different server altogether, but now you have 2 applications. And then let's say things change again. Now you want to show users recommendations for things to buy based on their purchases. So the team that's in charge of making recommendations, it's a bunch of data science-y people. They've only do Python, and it's a bunch of machine learning. So naturally, microservices. It just happens. But really, the answer often is services. As your engineering teams grow, your products grow, you don't have to be on a microservices bandwagon to find yourself in this situation. And a service might be written in a different language or have an infrastructure requirement that another service doesn't have. And as our web apps grow larger and larger, they start to look less like a garden, maybe more like a little collection of different plants in different kind of pots. And so you might find yourself needing to change your tooling. So where does distributed tracing fit into this bigger picture? So let's say one day your e-commerce page starts loading really, really slowly. And from the perspective of you as the e-commerce team, you can look in your application performance monitoring software like New Relic, something like that. You can profile your app with a profiling tool. And you can see this recommendation service, it's taking a really long time to return recommendations. So with a single process monitoring tool, all the other services in your system look just like third-party API calls. You're getting just as much information about calls to Stripe to charge users credit cards as you do a service that's run in-house by a different team. So from a user's perspective, you know it takes an extra 500 milliseconds to get recommendations, but you don't know why without reaching out to that team. They manage the recommendation service, so you have to get access to their profiling tools, you have to get time on their roadmap to start digging into your issue, and it becomes more and more complicated as your system gets more complicated. At the end of the day, you can't tell a coherent macro story about your application just by monitoring individual processes. And if you have ever done performance work, you will find people are terrible guessers. It's always the last place you look. You're like very convinced it's one thing, but a lot of times you have no idea where the bottleneck is. So what can we do to increase visibility into these systems and have a macro level story? And that's where distributed tracing can help you out. It's a way of commoditizing knowledge. Adrian Cole said this. He's one of the Zipkin maintainers, and he talks about how in these increasingly complex systems, you want to give everyone involved the tools to understand the system as a whole without having to have experts in each individual silo do the investigation. So this is awesome. Maybe you're like, cool, Stella, I'm on board. Let's do this. You've got your services, they're running in different processes. So why is distributed tracing not just like easy? There's a couple of different things. So one, a big thing for me was that it is not a Ruby thing. Like, the Ruby community doesn't talk a lot about tracing, and the people who are working in this ecosystem are largely working in Java, Go, Python, and so it's not that there isn't Ruby tracing, it's that a lot of the examples that you see online are written in other languages, and so that can be a bit of a hurdle. There's also a lot of domain-specific vocabulary. So reading through the docs can feel really slow, even if you're a very senior engineer. And finally, the most frustrating thing for me was that the ecosystem is very fractured. It's still changing pretty rapidly, and it's about tracing everything everywhere. So a distributed tracing solution has to support tons of different languages, different kinds of frameworks, and navigating all of those solutions to find which solution works for your company is not actually trivial. So how can you get past these hurdles? We're going to talk a little bit about theory today, about how distributed tracing works, about the fundamentals, and then we'll have a little short checklist for how you can maybe take this from theory to practice. So the basics. I'm going to start by talking about black box tracing. The idea of a black box is that you can't change anything. You don't even know about your system itself. You would capture and log incoming traffic and outgoing traffic at a lower level than your application, so like at the TCP level. And then all that data from your internal services goes into a single log, and then using this like magic of statistics, you can just guess the behavior based on log processing. But I'm not actually going to talk about black box tracing because for us at Heroku and for a lot of other companies, it turns out it's not actually a great fit. And we'll talk a little bit about why that might be. So one reason is that you need a lot of data because it relies on statistical inference. And also because it uses statistical analysis, there can be a delay in returning results. But the biggest problem with black box tracing is that in an event-driven system, so like let's say you use something like Sidekick to do a lot of async work, or if you have a multi-threaded system, you can't actually guarantee causality. And so what does that mean from like a code perspective? So there's like really serious papers written on this topic, so this is a very TLDR. But if you look at this simple example here, you've got service 1, it's going to kick off an asynchronous job, and then immediately you're going to make a synchronous request to service 2. So if there's no queue, no job delay in your queue, then the timestamps will actually look like service 1 calls async job, and then service 2 happens. But if that queue starts to have a delay, like you're simulating here with like a sleep 15, then based on your timestamps, it'll actually start to look like the second service made that call instead of the first service. So we can kind of solve this problem using something called white box tracing. White box tracing, it assumes that not only do you understand the system that you're using, but you're actually able to make changes to the systems themselves. And so we can be sure about this path that a request takes through your full system using something called metadata propagation, where we explicitly pass along information about where that request has been and where it's going. And that's a type of white box tracing. And another benefit is that it happens basically in real time. There's no statistical analysis being run. All right, this is your first test. Thank you. So let's do a little history lesson. So basically, I would say the most well-known example for anybody who starts to read about distributed tracing is Dapper. and the open source library that it inspired called Zipkin. The Dapper paper was published by Google in 2010, and it wasn't the first distributed system debugging tool that was ever built, but it was super interesting because it was the first one that had been running at Google scale for many years before they published the paper. And so it was able to show that this kind of tracing, that it wasn't just that it was viable, but that it was actually super valuable, and that Google found it that Google found it integral to their process. And so Zipkin came from that. It started as a Hack Week project. Twitter had a Hack Week, and somebody read the paper and was like, all right, let's just implement it here. It was open sourced by Twitter in 2012, and the project is currently led and maintained by Adrian Cole. And so from here on out, I'm going to use the term distributed tracing, and I'm going to use that to specifically refer to these sort of Dapper, Zipkin-like systems, because white box metadata propagation distributed tracing systems is really hard to say, and I will screw it up every single time. So we'll just call it distributed tracing. So if you want to learn more actually about stuff that's not about these metadata propagation systems, it just only took me once to fuck it up. You can actually look at this paper, and it has a really great overview of the different kinds of tracing that's out there. So how do we actually do this? I'm going to walk us through the sort of big major components that power most distributed tracing systems. First of all, we have the tracer. And that's the instrumentation you actually install in your application using Bundler with like a Ruby gem. There's a transport component, which takes the data that's collected in your application, transports it to a collector, which collects it, obviously. And there's a UI component that will take all that collected data and allow you to view it. So let's talk about the level closest to your application itself, the tracer. This is where we're actually tracing the individual requests. And it lives inside your application, typically installed using a gem, just like you would install like New Relic, and it'll monitor, it'll start tracing in your application. And a tracer's job is to record data so that we can tell the story as the request goes through each application. And you can think about that full story as a trace. So that request that we talked about earlier in our e-commerce application, that's all a single trace. And our next vocabulary word is a span. And a trace is made up of many spans, and they're each piece of the story. And in our case, with the e-commerce app, it calling out to the order service and getting a response back, that little bit is a single span. And in fact, any discrete piece of work, it can be even inside your service, you can actually trace your database calls, anything that's, anything that you're doing in your service can also be captured. It doesn't have to be network requests. So we want to start mapping out the system and really understanding what's happening, what kind of information we want to pass along. We could start with an ID. That's the easiest thing, and it says that this is trace 123, and that went all the way through our system. And you could query your logs later and see, oh, 123 did all of these things. But you're going to run into the same issue that you run into with black box tracing, which is that you can't guarantee causality strictly based on the timestamps of those logs. So you need to explicitly create a relationship between each of the components, and you can do that using a parent-child relationship. So the first request that comes into our system, it doesn't have a parent, so we know that's the top of the tree, that's the first request. And then when the auth process is going to talk to our e-commerce process, it's going to modify the request headers and pass along a randomly generated ID. And here I set it to the parent to 1, but it could be anything. And it's going to keep doing that with each request, passing it on to each instrumented system. And so a trace is ultimately made up of many parent-child relationships. And this relationship forms a directed acyclic graph. And so by tying all of this information, you're able to describe the system not just with like an image, like a chart here, but with a data structure. And we'll talk a little bit in a few minutes about how the tracer actually accomplishes that. So if all we wanted to know was the relationship, we just want to see that graph mapped out, you could stop there. You could say that's our trace, that's everything. But what you really want to know, like in your service world, is what's happening, what are the problems that are happening? And so by explicitly also passing along timestamp annotations, you can begin to understand things like latency in your system. And so hopefully you're not seeing like a full second of latency between each of these things. But let's look at how these annotations, these timestamp annotations, can fit into our system. So zooming in, zoom in and enhance, to where our auth process is talking to our e-commerce process. In addition to passing along the trace ID, parent ID, and the child ID, we'll also annotate with a tag and a timestamp. So the auth process is going to annotate that it sent the request. The e-commerce app is going to annotate that it received a request. And so you could compare the timestamps there, and you'll see you can see the network latency between the two. So if you had a lot of requests queuing up, you would see that time go up between them. On the other hand, if you compare the timestamp between server receiving the information and the server sending information back, that's going to show you how long it actually took to process the request. So if your app is really slow, that's where you would see your time start going up. And then finally, the client received annotation is just going to close out that span and say that it's complete. And then finally, this data needs to be transported so that you can look at it. And it's going to be sent via a transport layer to a separate application that's going to aggregate all that data and display it. So how is this not going to add latency to your system? First of all, it only propagates IDs in band, so it only passes along those IDs in the headers, but it reports out of band. So if you're familiar with things like Librato, any kind of metrics gem, they're going to use an additional thread to communicate with the system so that it's not blocking your requests. And Zipkin is going to do the same thing. It uses the sucker punch gem to make a threaded call out to the server. And then finally, it's ready to be viewed in a UI. What is that really going to look like? So this graph earlier is awesome at actually showing us the flow of the request. It actually is really good at understanding how our systems are connected, but it's not really actually good at solving latency questions in our system. So distributed tracing systems use swim lanes or Gantt charts instead. So the open tracing documentation is a really good example of this. So this is a similar request tree to the one that we just had. But if you look at it in swim lane or Gantt chart format, you still see the different services, but the visualization is now helping us see how much time is spent in each sub-request, in each service that's talking to each other. And you can also, like I said earlier, instrument and visualize internal calls that are happening inside of a service. Like all of those gray bars, that would be things that are instrumented inside the same service. And so you can see here that the billing service, the green box, is blocked by the authorization service, which is the red box. You can also see threaded or parallel job execution inside the resource allocation, those gray boxes. And if you see one of those bars widening, like the red bar widening, it would mean that your service itself is getting slower. If you start to see a widening gap between two adjacent blocking services, that could mean that there's queuing behind other network requests. Bless you all. All right, so now we talked about what we want. Like that's kind of what we want to see. How is it done? We know at a minimum we want to record information when a request comes into our systems and returns information back to our users. So how do we do that programmatically? Rack. I love Rack. Middleware is a pretty common way. If you're running a Ruby app, you'll probably be using Rack. So Ruby uses this interface, if you're not familiar with it, called Rack, that servers and applications can use to talk to each other. Sinatra, Rails, they both use Rack. It serves as a single entry and exit point for client requests that come in and out of your applications. And it allows us to add middleware, which would sit between your server and your application and allows you to customize requests and responses. And since we want to manipulate those, this is a great place to put it. So don't worry too much if you're not super familiar with what a Rack app looks like. This is kind of a TLDR, but your middleware is gonna mimic a Rack app. So it's a Ruby object. It responds to a method called call. Takes one variable called the environment hash, and in the end, like the most important thing, returns a response, which is the status, the headers, and the body. And middleware is formatted exactly like this, so that you can insert middleware, and each piece of middleware will act basically exactly the same and pass your request all the way down. So let's do a little pseudocode for our middleware. that we want to do for some tracing. So we'll have a method called trace. It'll take a block, and it'll do some tracing. So what does that tracing method look like, potentially? So our trace method, it's going to start a new span on every request, because we want to tell a new story for each service that we're talking to. It's going to record that it's received that request with a server received annotation like we talked about earlier. It's going to yield to the rack app so that it actually does everything that needs to happen, that it actually talks to your application. And then it's going to come back and, in the end, ensure that, that we record that the server sent information back to the client. So this is pseudocode, but if you actually want to see a really great example of what this looks like, the Zipkin documentation, or Zipkin code is all open source, and it's super easy to read, and it's a great implementation of a rack tracer. So we would tell our Rails app, our Ruby app, to use our middleware, and it will instrument all the requests that are coming in and out. You never want to sample every request. That's the one thing that kind of trips people up about distributed tracing, especially if they're working in, they want to see every single request and drill down and look at every single one. That's not what it's for. It's really about sampling, and you can either really slow down your application, or much more likely take down your distributed tracing infrastructure if you send every single request. I would not know that from experience at all. So you're going to want a sample rate. 0.1 is kind of where people start, but always err on the side of the lower sample rate and move it up if you need more. So we've got our requests that are coming into our system, but in order to generate that full relationship, we also need to record annotations on the requests that leave our system. So these could be requests to external APIs like Stripe, GitHub, whatever. But if you actually control that next service, if somebody at your company controls that next service, you'll be able to actually explore deeper and deeper into that tree if you instrument each of the apps that your service is calling. So how would we do that? Middleware. Love you, Middleware. Thank you for all that you do for me. So if you're using an HTTP client that supports middleware, it's pretty easy to incorporate it into your application. So I'm going to use Faraday as an example because it's pretty similar to the structure of a rack middleware. So it looks pretty familiar. You're going to pass in our HTTP client app, do some tracing, whatever that is, and then keep calling down the chain on our middleware. So the tracing on this side, though, is a little bit different because you're going to want to actually manipulate the headers to pass along the tracing IDs. And that way, if you're calling out to an internal service that's already been instrumented, that internal service will know, oh, I'm being traced. I know how to trace. Let's keep this party going. But then if it's not, if it's like GitHub or Stripe, a third-party API, they're just going to ignore your headers, and you'll be able to just see the start and end. And so each of these colors would represent an instrumented application. And so with the incoming instrumentation, we record the server send and server receive. We also want to record that we're starting a client request and ensure that we are receiving a client request. And like we did before, we're going to add in our middleware, so add it into Faraday here, and it'll start tracing. So these are some of the basics around how distributed tracing works. Let's talk a little bit about how you can choose the tracing solution that's right for you. I don't actually have any answers, spoiler alert. I wish I did, that I could just tell you that this is a really easily solvable problem, but this is actually the harder part. But this will help you at least be more aware of some of the issues and trade-offs you might need to work through. So the first major question is how do you get this working? And this ecosystem is changing constantly. Even since I wrote this talk, new tracing infrastructure has come out, has been introduced into the community. So, buyer beware if you're watching this at home in 6 months, that things might be a little different. So should you pay for an out-of-the-box system? Yes. If you can afford it and you don't have a team to run it, yes, do it. It's always nicer if you can afford to have other people run software for you. There's a couple. There's Lightstep, Traceview, or two that come to mind, but your APM provider might actually have a distributed tracing solution. You may want to adopt an open source solution. If you have people on your team who are comfortable with the underlying framework and you have capacity for managing infrastructure, this might be a good fit. This is what we ended up doing, partially because it's really nice to run stuff on Heroku, and Heroku makes it really easy. So for us, running that additional infrastructure wasn't a problem. So it took us a couple months of part-time work on our team before to get things up and running, but that was also while doing a ton of other stuff. So your mileage may vary. The main open source options are going to be Zipkin and OpenCensus, which is kind of came out of the Google ecosystem. And one thing that completely tripped me up and made me really crazy for the first little bit when I was looking at this is what about open tracing? Everybody's talking about open tracing. If you do any research into distributed tracing, people are talking about it constantly. And the thing that I didn't understand, it took me a while to get, was that open tracing is not like Zipkin. It's not an implementation. It's not something you install and it's tracing for you. It's actually an API. So it's a way to standardize instrumentation across tracing providers. So if you wanted to switch from an open source provider to a paid provider, or another paid provider to a different paid provider, the idea is that instead of having to redo all of the tracing work that you've done, you would just install a different gem with Bundler, and it would magically work, right? And that sounds very awesome. And in theory, that would work because your paid provider and your open source provider would be good citizens. They would conform to this API. Everything would be great. In practice, it hasn't been 100% adopted. They've published a number of APIs for each language, which is great. But then each tracing provider has to actually change their API to conform to that API. So for example, there's a Ruby API in open tracing, which is really cool. But only Lightstep, I think last that I checked, actually uses that. So things like Zipkin, they haven't actually built a bridge between their existing implementation and the API that open tracing recommends. And it also doesn't standardize interoperability. So for example, if you end up using a tracing provider, an open source tracing provider for all of your Ruby apps, and you need and your Go provider is a paid provider, you can't just have both of those send data to your open source system or your paid system. They're not interoperable. And another thing to keep in mind, going beyond open tracing, is that when you look at these solutions, open source or hosted, language support is very broad. So at the minimum, it just means you can start and end a trace inside of a Ruby app. So a provider might say, oh, we support Ruby, but you'll need to write your own rack middleware. You'll need to write your HTTP library middleware, which is not a deal breaker by any means. It's not the end of the world, but it is extra work that you might not be aware that you're signing up for. And then you'll need to actually rinse and repeat that process for every language that your ecosystem has. So if you have Go apps, Python apps, they'll all need to come into this matrix. Some big companies are building their own. Etsy and obviously Google built systems in-house. But I would say for the most part, even companies that started out building things in-house are trying to feed back into the ecosystem and contribute to open source solutions. And if you're curious, if you like to rubberneck like I do on other people's software, somebody actually wrote a paper about it. There's 26 companies and what they're using for their distributed tracing tools that they use. Largely Zipkin, internal solutions, open source solutions. But like all software, it is already out of date, even though it was published like 9 months ago. Another thing as part of your checklist is just your infrastructure requirements. Like, does your ops team have any concerns about maintaining a new kind of infrastructure? And you also need to make sure that all of these different things, the tracer, the transport layer, the collection layer, all of these things are compatible with every service that you want to implement. And so for us, conference bingo. So for my team, we're a Ruby team. Like, we almost entirely program in Ruby, but we run a Java service, which is Zipkin. And it's pretty different. So thank God for Yannick, Java Yannick. If he ever sees this video, he's going to be so mad at me for calling him that, because he's like the only person who can really get deep into the Java, and we love it. But yeah, you have to be comfortable with running something that maybe is not your wheelhouse. And then finally, there's like a really random thing, which is that some tracing solutions require you to run a separate collection agent on the actual host, like the actual box. And that for us is a total deal breaker because we don't want to do that in our Heroku infrastructure. And so just make sure that you're not required to run something as root on all of your boxes, because that was a big surprise for us. It's not a Zipkin thing, but it is a thing for some providers. You also need to figure out how you can secure who can submit and see data inside of your system. Zipkin doesn't have built-in authentication and authorization, so you can run it inside a VPN, or you can use a reverse proxy for authentication, which is what we ended up doing. We couldn't just let people just send data to our Zipkin, so we use basic auth with htpasswd to do some team-based credentials. This is definitely the intermediate level distributed tracing talk, but it might come up for you. We also needed to add in our own browser authentication because we didn't want anybody on the internet to be able to see the UI. So we use Bitly, their OAuth 2 proxy in front of our Zipkin web UI. It worked really super well so that we could limit it to people with Heroku.com or Salesforce.com email addresses. But even with a hosted route, you have to ask, how do we control access? How do we get it to people that need it? And if your organization has PII, any kind of really sensitive data, keep an eye out for at least 2 security issues. One is custom instrumentation. So if you try to instrument something inside of your application, like Postgres, and you're logging SQL calls, be careful that when you do custom tracing that you're not accidentally sending PII, like personally, is that a thing here? Personally identifying information to your Zipkin or your distributed tracing provider, because that's not awesome. And you need to know what happens if we do leak it. If you're using a third-party hosted service, how are we going to know that you've deleted this? And if you're running it yourself, how can you wipe the data? And the last thing to really consider is the human side of this is distributed tracing. The nature of distributed tracing is that the work is also distributed. And so there's cognitive load to getting everyone on board and understanding how this works. If you're distributed across time and space like Heroku IR, it can be really hard to get people really all on board across the organization. Set yourself up for success. Don't do what we did. Get it on the roadmap, or you'll be opening PRs on Teams, which we're happy to do, but it's maybe more work than you're expecting. This is the full checklist. I'll tweet out these slides later, but hopefully this will help give you some questions to ask yourself. And you might actually be thinking this is just TMI. This is way too much information. Where do I start? We're talking about vendors and deleting PII and things are terrible. My advice is if you have some free time at work and you're really curious, try running Dr. Zipkin. It has a test version of Cassandra built in. So you need to get the Java app up and running, but it's relatively easy and you can get it deployed on Heroku, And I really didn't mean that to be a plug. I just mean if you want to play around with it, obviously it is something you can run on Heroku. We do. Try to instrument an application just that makes one API call. It can be an external API call, but just try instrumenting just one application, and it'll help you be a little bit more fluent with how all of this works. And one final Heroku plug for your Heroku swag. I also just want to say a big thank you to Heroku for helping me get here. We've also got another Heroku other than Amy who will be with us at the party tonight, who's actually in our Sydney office. So if you'd like to talk businessy Heroku stuff, he's definitely your guy. Thank you.